Okay, hello everyone. In this lecture, we will see the designing of Murray model for the detection of 101 using D flip-flop. And here we will see the condition of overlapping detection. So, as you know, for designing the Murray model, we have to follow 4 steps. First step is the designing of state diagram. In the second step, we will see the designing of state table, and also we require the excitation table of D flip-flop because we are designing by using the D flip-flop. If you are designing the Murray model by using the JK flip-flop, in that case you require the excitation table of JK flip-flop. Now, in the third step, we will use K-map to find out the output for in the terms of D1 and D0, or in the terms of D flip-flop. In the last step, we will design the circuit diagram. That is our 4 steps. And for this question, we start from the first step, that is the designing of the state diagram. So let's see how we can draw the state diagram for 101. So in the Murray model, we represents the state along with the output. So here it is represented as state divided by output. In between, we write down the input, and then again we write down state by output. This is the difference between the Murray machine for the if you compare with a Mealy machine. In the Mealy machine, we represent state, to state, and in between we write down input by output. This is the difference. This is the Murray model, and this is the Mealy model. So this is the actual difference between the Murray and Mealy model. Let's start a state diagram for 101. In the case of overlapping, so always we initialize the state diagram from state A, and we write down the output along with it. So this is the state A and the output is 0. It's the initial condition, and we are detecting 101. We have not received the correct pattern. If we receive single bit correct, then I will move to the another state B. So here you write down input is 1 and this is the output 0. Why? Because we have not received the correct pattern till now. If after B, if I receive next bit correct, that is 0, I will move to the C state, and here also your output will be 0 because we have not received the correct pattern till now. After this, if I will receive 1, so now this is 101. So I will move to the D state and my output become 1. Why? Because now I receive the correct pattern. So this is correct for the correct pattern. But of course, at every state, there is a chance of incorrect inputs. So for example, you are in the state A and you are getting 0 as a first bit. If you are getting 0 as a first bit, that means 0 means what? We have not received a single bit correct because my first bit is 0. I will remain in the same state, and here I will write down input 0 because if input is 0, I don't have a single bit correct. Now, for example, you are in the state B, that means I have a single bit correct B. Sorry. If I will receive 0, I will move to the state C. But what will happen if I receive 1? If you are receiving 1 also, that means I have a single bit correct because after that I want only 0, 1 for the correct patterns, right? So here I can say if you are getting 1, you have to remain in the state B because B is the single bit correct state. Now, if you are in the state C, if you C means what? 2-bit correct. That means I already have 1 0. If I will get 1, I will move to the D state. But what will happen if I get 0? 0 means what? Complete loss of pattern because after that again I want 101 to detect the correct pattern. So that means it's a loss of pattern, and I will move to the initial condition if I will receive 0. Now you are in the state D. State D means what? You already received 101, right? Now, if you receive 1. Then what does it mean? It means that I have only a single bit correct, because after that again I require 0, 1, right? Single bit correct state is B. Okay, single bit correct state is B. I will move to the B, and here I will write down 1. If I receive 1, I will move to B. But as this is a overlapping patterns, 1 0 1 0 1, that means there is a chance of a single bit overlap, right? If there is a chance of single bit overlap, that means you have to skip two state, 1 plus 1, 1 because of overlapping bit. So we have a single bit overlapping plus 1. So that many state you have to skip from the beginning. So we are skipping one state, two state. So here you have to jump to the C state if you are getting 0. If there is a chance of 2-bit overlapping, in that case you have to skip 3 state from the beginning. Clear? If there is a chance of a single bit overlapping, then you have to skip 2 state from the beginning. If there is no chance of overlapping, then you have to skip only a single state. That's okay. Now this is the complete state diagram for 101 overlapping case. Now we will see the state table using this state diagram. So here in the state table, we require these parameters. This is the present state. Then we write down inputs. Input will be represented by X. Then we will find out next state. And then this is the output Z. These are the requirements for the state table. I'm making a blocks so that we can fill along with by using the state diagram. So as we have seen, how many states are there? We have 4 states, A, B, C, D, right? So that means here you have to make 4 blocks, 1, 2, 3, 4. Because we have 4 state A, B, C, D, I'm writing A 2 times. Why? Because if you are in the state A, there is a probability of getting either 0 or 1, right? If you are in state A, you can receive 0 or you can receive 1, right? So there is 2 types of input possible. That's, and you know, in the truth table you have to write down all the possible combinations. So here either 0 or 1. Similarly in B state also there is a possibility of 0 1 as an input. C 0 1. In the D state also there is a possibility of input 0 1. Now, if you are in state A and you are getting 0 as an input, what will be the next state? See here in the state diagram, if you are in state A and you are getting 0, you will remain in the same state A. And if you get 1, you have to move. If you are getting 1, then you have to move to the B state, right? So here you write down A, if B. If you are in state A and you're getting 0 as an input, the next state will be A only. If you are in state A and you are getting 1 as an input, the next state will be B, right? Same thing we have to see for B state. If you are in the state of B, then if you are getting 0, next state will be C. And if you are getting 1, next state will be B only. So CB. It is C and this is B. Now same you have to check for C. So if you are in state C and you are getting 0, 1, for 0, you have to return back to A. 1 will give you D. So AD. This is A and this is D. From D also we will check if you are getting 0, what will happen, and 1. So if you are getting 0, you have to move to C state. If you are getting 1, so B state. So CB. So CB. So CB. So now we have written all the state. As you know that in the digital system, we cannot represent anything by using the alphabets. So now here we will use the binary number to represent every state. And as you can see, we have only 4 states, and 4 state can be represented with the help of only 2 bits. So how we are representing? We are representing A as by using 0 0 and B by 0 1. So this is A as 0 0, B as 0 1 0 1, C as 1 0 1 0, D as 1 1 1. Similarly, here A will be represented by 0 0, B will be represented by 0 1, C by 1 0, D by 0 1, A by 0 0, D by 1 1. C by 1 0, and B by 0 1. Now we have to write down the output. As you can see in the state diagram, output is represented here only. At every state, output is 0, except in the D state. That means the output become 1 whenever you move from D state to any other state. So if you are moving from D to B, then also your output is 1. And when you are moving from D to C, then also your output is 1. So here, whenever you are moving from D state to any other state, either on C or B, your output become 1. For rest of the conditions, it will be 0. Right? So now we receive the output. Now, after that, we have to decide whether which type of flip-flop you are going to use to design the Moore model. For example, we are using D flip-flop for designing. So for that, we require the excitation table. Excitation table of D flip-flop. Excitation table of D flip-flop. Right. So here I am writing the excitation table. This is Qn. This is Qn plus 1. This is 0. 0 0 1 1 0 1 0 1, so it will be 0 1 0 1. So the good thing with the D flip-flop is whatever will be your next state, it is similar to the value of D, right? Now here you see in the state table, I am assuming this is Q1 and this is Q0, as this is the present state. I will represent Q1 plus 1 and Q0 plus 1 just to tell that these are the next state for this present state, right? So this is Q1, this is Q1 plus 1. So now you have to compare Q1 and Q1 plus 1 and find out the value of D1. Similarly, after comparing Q0 and Q0 plus 1, you will get D0. How you have to compare? You have to compare by using this excitation table. This is called as the present state. This is called as the next state, and you will get the value of D, right? Now, the good thing is whatever is your your next state, it will be similar to that of D. So if you are using D flip-flop, you just write down T1 as your Q1 plus 1. So whatever is your Q plus 1, 1 plus 1, it is similar to your D1. So now here 0, 0, 1, 0, 0, 1, 1, 0. Right? Similarly, what will be the D0? D0 will be getting after comparing Q0 and Q0 plus 1. By the excitation table, we know that whatever is your Q0 plus 1, it is similar to that of D0. So it will be 0, 1, 0, 1, 0, 1, 0, 1. Now, this state table is completed along with the excitation table. Now we will make a K map to find out the expression for D1 and D0. So this is the K map, and for D1, I have to draw the K map. First, we will decide how many variable K map is required. So now you see in the input part, we have Q1, Q0, and X. These are the three input. So first, you have to draw the three variable K map for finding the expression for D1. So this is Q1, this is Q0X, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, right? Now, wherever your function value of D1 is 1, that means for these three conditions, you have to fill the K map. That means for 0, 1, 0, for 1, 0, 1, and for 1, 1, 0, you have to fill the K map by 1. So this is 0, 1, 0, this is 1, 0, 1, and this is 1, 1, 0. So now we filled it by using wherever your function value was 1. Now you have to make the group here. So one group is possible like this and one individual term. So now the value of D1 can be written as Q1 Q0 X plus Q0 X bar. So this is the expression for D2, D1, D1. Now we will find out the expression for D0. So again for D0, we have to make the three variable K map, because here also your input will be Q1 and Q0 X. So here I am writing like this. This is Q1 and this is Q0 X. I am taking 0, 1 here. This is 0, 0, 0, 1, 1, 1, and 1, 0. Now wherever your D0 is 1, you fill this K map or that. So here you can see this is 1 for this conditions, this condition, this condition, and this condition. For this condition, the value is 0, 0, 1. For this condition, it is 0, 1, 1. For this condition, it is 1, 0, 1. And for the last condition, it is 1, 1, 0. Now, we have to fill this K map for these values. So here you can see it is 0, 0, 1, 0, 1, 1. This is 1, 0, 1, and this is 1, 1, 1. Now, if you see, we can make a group like this. And for this group quad, the expression will be X. Similarly, we have to find out the expression for Z. And for Z also, we have to make a 3-variable K map like this, where the inputs will be Q1 and Q0 X. As it's using the gray code, we can represent it as 0, 1, 1, 1, 1, 0. Now, wherever your Z values are 1, you have to fill the K map by 1 there. So here it's 1 for these two conditions, 1, 1, 0 and 1, 1, 1. So now you see in the K map how I am filling it. It is 1, 1, 0 and this is 1, 1, 1. And we can make a pair like this. And the expression for Z will be equals to Q1, Q0. Right. So now we have all the expression and we can go for the circuit designing. I'm writing the expression here. We got the expression for D1 as Q1 Q0 X plus Q0 X bar. Similarly, I calculated the value of D0 as X and we calculated the value of Z as Q1 Q0. Now, as we have seen, we have used two flip-flops for that. Why we use two flip-flops? Because we use two input bits for representing the state. As we are using two bits for representing the state, that's why we used two flip-flops. So in the circuit design also, will start by drawing the two D flip-flops here, back to back, one here like this, one at the top, another one at the bottom. And here I am writing this is the first flip-flop and this is the second D flip-flop. Here we have to write down this is D1 and this is D0 here. And then we have to provide the same clock to all the flip-flop because it's a synchronous circuit, right? From here, we will get the value of Q1 and this is Q0. And here the value of D0, D1, D0 we calculated as X. D1 is represented by this expression. So here I am giving it like this, and that is given to one OR gate. Here the three terminals are there, Q1, Q0 bar, and this is X. This is Q0, this is X bar. Similarly, Z will be represented by Q1, Q0, so that you can design by using the AND gate. So this is the final answer in the case of 101 Moore machine overlapping.